Okay, picking up on the second page, we're going to evaluate line integrals where our curve might be a union of some smooth curves that we've listed below. They might be semicircles, line segments, parabolas. All we have to do is break up our line integral into however many smooth curves we need. So let's take a look at that. Example 2, we're going to do the line integral of 2x ds, but we're going to begin with a parabola. Y equals x squared. However, we're looking at just a piece of that. We're going from 0, 0 to 1, 1. Now with y equals x squared, this is going to be our first part of our curve. We could write it parametrically by letting x equal t, and if x is equal to t, then y would equal t squared. Now notice the advantage to doing it this way. Letting x or y equal t will very quickly just allow you to plug that t value into the equation and find another parametric equation for our second variable. But if x is t, you can see x is going to vary between 0 and 1. And very fast we can also see that dx dt, we're going to need this in a moment, is a 1. And dy dt is going to be 2t. Well, just turning this line integral into an ordinary integral, we're going to integrate between 0 and 1, and then 2, and x, of course, is just going to be t. But ds, now ds, I hope you recall from the front page, was the square root of dx dt squared plus dy dt squared. All of that inside your square root, and then we even have a dt after that. Well, if we were to substitute all of that in, hopefully you can see that we'd get 1 plus, now 2t would go in here, 2t squared would be 4t squared. So look at that. We now have an integral like we saw in AB calculus. And for the sake of time, we'd like to see if we could do this video very, very fast to avoid having to have a second video added. Beyond that, you could let your 89 evaluate this integral very quickly. You'd get 5 root 5 minus 1 all over 6. Now please understand that this is just what we'd call C1, the first part of our curve. It's the parabola, the parabolic part, and there's a second part, a second component, and that's a vertical line segment from 1, 1 all the way up to 1, 2. Now from here, again, getting the parametric equations might be, the most important part, and the part that's going to take a little getting used to. Notice that when we're on a vertical line segment, your x is always fixed. It's x equals 1. Your y value, though, I'm going to let equal t. And our y values vary between 1 and 2, so we're going to use this equation right here. So finishing up our line integral, we can say, well, let's see, we're going to go back just to an ordinary integral with respect to t. We're going to integrate from 1 to t. But now look at this, our x, this is 2 times just a 1. And then ds, well, ds, if we were to look at dx dt squared, well, my goodness, that's 0, isn't it? You can see that very quickly. That's very nice, that dx dt is actually just a 0. And in fact, dy dt is going to be a 1. So we'll say dy dt squared. Well, we're going to be squaring a 1. So do you know what this really becomes? This square root, this arc length, really is just a 1 itself. Here we could just take an antiderivative. 2 times 1 is 2. We'd get 2t, and we'd evaluate between 2 and 1. I think it's quicker to do this by hand. And we'd get 2 times 2, which is 4, minus 2 times 1, which is 2. That's just a 2 itself. So we have this for C2. Well, what's our final answer? Well, of course, we're going to have to add these two together. Here's your C1, here's your C2. And your final answer then is going to become, well, this is really 12 over 6 for 2. So you'd get 5 root 5 plus 11 all over 6. Okay, well, what else can we do? Well, we can have applications of last chapter as well. We could find mass if we have a density function, which we have with rho here. We could even find the center of mass if that's ever applicable with x bar and y bar, very similar to what we did before. But let's take a look at example 3. And in example 3, it should look very, very close to example 1. We had x squared plus y squared equals 1 with y just above 0. So my goodness, what we could do again is just let x equal the cosine of t, let y equal the sine of t. Wonderful to have that. And you might even remind yourself as to what we saw before. We saw that ds, if you want to look back to example 1, this radical just became a 1, didn't it? I'm going to scroll back real quickly just to help you out and remind you of that. You can see that when we were here, this is literally going back. This is at least with x squared plus y squared equaled 1. We saw that this radical right here, when we took our derivatives, all of that collapsed to just sine squared plus cosine squared inside of our root. So it completely goes away. That's wonderful. We're going to use that fact to maybe streamline everything just a little bit. We'll say that ds is just going to equal dt. But it does say that as we continue reading on, this is just our curve that we're integrating over. This is a wire, actually. And this wire that's going over our curve is thicker near its base than near the top. We want to find the mass of the wire. If the linear density, if rho, is proportional to its distance from the line y equals 1. So up here is a y coordinate of 1. And here is the line y equals 1. Let's just say that we have an arbitrary point, like right over here on the wire, x comma y. The distance from that point to the line y equals 1 is only measured vertically. It's only measured from y equals 1 to the y coordinate. So this distance that we're seeing right here would be 1 minus y. Whatever our y coordinate is, it's that far away from y equals 1 itself. And that means that rho, our density function, is proportional, so take k times something, k times the distance. So look what we're really going to do here. We're going to work out and say that our mass is equal to this line integral of k times 1 minus y ds. And that's really what we've got right here. But like we said, we now have our parametrization. We already know that's coming from example 1. We know that our t value was between 0 and pi, so we could go right back over there. Here we have k times 1 minus, but our y is going to be sine of t. And ds, remember ds is really the square root of dx dt squared plus dy dt squared. We can't forget that. That was our arc length link. But we just showed from example 1 that that just becomes dt. So here we go again. This mass, honestly, is just a Calc AB problem. Let's factor out a k and simultaneously take antiderivatives. The antiderivative of 1, of course, is just going to be a t. And then the antiderivative of negative sine would just be plus cosine. And again, if you're ever doubtful about that, take a derivative real quickly. The derivative of t is 1, derivative of cosine is opposite of sine. Do your fundamental theorem, and you can see what's going to happen. You'll get pi plus, well, the cosine of pi is going to become negative 1. We'll work that out. The 0 part, oh my goodness. Don't think that the 0 we can just ignore. The t equaling 0 is going to cancel out, but the cosine of 0 is 1. So my goodness, do you know what you really are going to be left with is k times, well, minus 1 and another minus 1 will be minus 2. This is your mass. And that's, another application that we could have. Okay, well, we could at least get started talking about our final part of the lesson. The line integrals studied so far always were with respect to arc length, ds. And we had that link with the square root of dx dt squared plus dy dt squared, and then we had dt after that little change, that little substitution. But of course, a line integral, in theory, you could say, well, what if I just wanted to evaluate it with respect to x? And you can think, well, rather than ds, what if I just put dx? Well, remember that x was always equal to some function of t. So if I took a derivative with respect to t, I'd have dx is equal to x prime of t dt. So this dx is going to get substituted right over here with x prime of t dt. Very similarly, we could say that, well, y could also equal some function of t. dy then would be y prime of t dt. So we could replace a dy with y prime dt. So that's really how we could begin to work something like that out. Well, let's take a look at our last example, number 4, at least begin to set it up. Now look, we have two different parts. It says, evaluate this line integral. But my goodness, we're going to go from 1, 2, 3, 4, 5 steps to the left, down 3. That's over here. And it's a line segment going to 0, 2. And we could say, well, here we have it. Just a plain, simple line segment. Could we evaluate this line integral? And guys, in all honesty, maybe the biggest important step is to go back to our beginning of our study with vectors, where we wrote equations of lines parametrically. And we were able to do that with a head minus tail kind of perspective for a direction vector, and we always started somewhere. We're going to be picking up with this in our next video as we wrap up this lesson. A little bit long today, but hang in there, we're almost done.